Hi, my name is Kartik and I am a PhD student at IIT Jodhpur. In this presentation, I'm going to talk about PhygitalNet, Unified Face Presentation Attack Detection via one-class isolation learning. So, in a journal pipeline of face recognition system, we have a user whose image is captured by a camera sensor, and then in the face recognition module, matching is performed. Now, a lot of attacks can be performed in the system. They can either occur at a camera sensor level or some altered image can be uploaded through some web portal. In this work, we consider two kind of attacks. One is physical attack and other is digital attack. For physical attack, we consider various kind of attacks like print attack, 3D mask attack, silicon mask attack, replay attack, etc. And for digital attack, we consider deepfakes, face-to-face, face swap, neural textures, etc. In this work, we objectify building a unified attack detection system which is robust against digital and physical attacks. So, to solve this problem, we begin by asking a question that what is common between both the kind of presentation attacks. So, in all the attacks, we realize that bona fide class is something common that is always going to be there irrespective of the attack modality. So, how about we isolate this bona fide class away from the attack class? One issue we would face to do that is the occurrence of covariate shift that would occur between the bona fide samples coming from different attack modalities. For this, we perform a pretext task where we combine the bona fide samples coming from coming from physical attacks and digital attacks, and then we tend to reduce the distance in the feature space. The other issue that we would face is pulling closer the bona fide samples to form a hypersphere. To address that, we train our model on the combination of physical as well as digital attacks, and we train it using a center loss. So for that, a center is initialized which pulls all the bona fide samples closer to the center. The next problem would be to push away the attacked samples out of the hypersphere. For that, we make use of a triplet loss where we set the radius of the hypersphere as alpha, and all the attacked samples inside the hyperspheres are pushed away using this triplet loss. So to put together the entire pipeline, first we perform a pre-training step where we combine just the bona fide samples from different attack modalities, and we try to reduce the distance between them in the feature space to mitigate the problem of covariate shift. The weights learned from this task are transferred to the downstream task where we combine the entire data set of physical as well as digital attacks, and there we train our model on the proposed solo loss, which is a combination of center loss and triplet loss, objectify to pull the bona fide samples closer to the center and push the attacked samples out of the boundary. We perform different kind of experiments to check the performance of our proposed algorithm. We've performed two baseline experiments as well. The first baseline experiment was to train our model end to end on the combination of all the data sets, and these are the performance that we achieve. The other experiment was performed where we assembled two models, where the first model focused on the physical attack and the other model focused on digital attack. Then we also performed ablation experiments, and we noticed that the proposed algorithm consistently performs better on individual attacks as well as on the unified attack. We also compare the performance achieved by the proposed algorithm with existing state-of-the-art techniques. From the table on the left, we see that we achieve comparable performance on both the attack modalities. However, we would like to make note that the performance reported for the existing techniques, these techniques train their model on a single data set and then test the model on the same. However, for our technique or for our algorithm, we train our model on the combination of all the data sets and then test individually on each of the test set. On the table on the right, we design a protocol for zero-day attack where we train our model on physical attack and then test on the digital attack, and also in the second experiment we perform the vice versa, And we also noticed that consistently we achieve better performance than the existing state-of-the-art technique. And when we also test our model on the combination of physical and digital attack, we perform significantly better. This is the t-SNE plot obtained in different settings. So in the first graph, we train our model, we train a ConvNet end-to-end only using a BCE loss, and this is the obtained t-SNE plot. When we start to train the ConvNet on BCE loss with solo loss, we notice some kind of cluster formation of the bona fide class. The red color corresponds to the bona fide class and the blue color corresponds to the attack class. When we perform pre-training, we see that there is an immediate formation of clusters, and where we can see two clusters of the bona fide class and two clusters of the attack class. Excuse me. And when we plot the t-SNE plot of the proposed technique, we see the formation of clusters as well as the separation, a very fine separation corresponding to the performance achieved. So to conclude this work, we conclude by understanding that we can actually train a single model for unified attack detection system. This proposed model is easier to deploy because now we need only a single model which can generalize over any kind of attack out there. We do not need an ensemble of the models anymore. As well as we also notice that pre-training contributes significantly to isolate the bona fide class far away from the attack class. We also understand from the experiments that our proposed algorithm can easily be extended to zero-day attacks as well. Thank you, and if you have any question, you can reach me out at my email ID.